Hi and welcome to Module 8, applying chemical ideas or our analysis of chemical ideas. So what we're looking at today is gravimetric analysis. Now we've done this before. It was the very first thing that we did really in Year 11 course, and we've been using the same sort of calculations regularly throughout the course, but this time we're looking at, instead of finding out just what percentage or what amount of a substance there is, we're actually looking at it now in terms of ions, so inorganic ions in particular. So the outcome that we are looking at is conduct investigations, which we're in the process of doing in class, and or process data, so using questions and using the information in those questions that are related to gravimetric analysis. So you will remember from Year 11, or hopefully you will remember from Year 11, that we are looking at gravimetric analysis, which is a technique that allows us to find out the composition of a mixture. So we separate out all the different components and then weigh them, and then we can work out the percentage composition by weight of those elements there. In this one, what we're looking at is the species that we're actually wanting to analyse must be separated from the rest of the mixture. So our aim is to form a precipitate to separate one of the ions. So in the case of the one that we're doing in class at the moment, we are looking at the sulfate component in ammonium sulfate. So ammonium sulfate is a common ingredient in fertilizers. We've got ammonium sulfate as a solid, and so we need to separate those sulfate ions. So by dissolving them into water, we are then separating the ammonium and the sulfate, but there's still ions in solution, so we need to find a way that we can precipitate out the sulfate ions. So we do that using a barium chloride solution. So we'll add excess barium chloride to make sure all of the sulfate has actually precipitated out, and then we can conduct our gravimetric analysis from there. Now, where could we use this? Obviously, we're looking at how we can apply these chemical ideas that we've been learning about through our chemistry course, and obviously we're looking at where can these be used in industry. So we can look at these for our mineral content of ores, which is quite important in the mining industry. They're wanting to know, well, is there enough of the ore that they're after that warrants spending a lot of money to mine that area to achieve that? We can look at what chemicals are dissolved in water, which again is important with water analysis to see what ions are actually in that solution. But this is a quantitative measure, not just qualitative. So we're not just checking what ions are there, but in actual what concentration. Nutritional testing with food. How do we know how much sugar is in there, carbohydrates and so on, compositions of soils, purity of our products such as our medicines and so forth. So many techniques that it can be used for. So our chemists use this all the time to test a wide range of substances, and it's a reasonably inexpensive process. But since the introduction of some modern techniques, gravimetric analysis has been largely replaced by other faster automated techniques. But it's not useful for all compounds. For example, when both the anion and cation are soluble, it obviously is going to be difficult to determine them there and the difference between them. So one of the things you're going to need to be looking at, particularly with the experiment that you're currently conducting, is the validity of the experiment. And that's obviously going to depend on a number of factors. And with our validity, we've got to make sure that one, all of our barium sulfate precipitates out. So that happens by adding excess barium chloride. We need to also make sure that all of that precipitate was actually collected by the filter paper. So what you'll probably notice is, A, did it all precipitate out? Did it get into the filter paper? Because it's such a fine precipitate, did it go through the filter paper back into the solution? So we need to make sure that all those sulfate ions were removed by solutions. So we can improve some of those things by doubling up our filter paper, using extra fine filter paper, doubling it up to make sure that we actually don't lose. So if you imagine we've got a grid sort of this way and the ions can get through, and another this way, we're reducing the likelihood that they might fall through. We need to make sure that the samples are totally dry, so we don't want any water there affecting our results. And also looking at when we're rinsing our precipitate out of our solution and out of all of our equipment, sometimes when we're pouring out the precipitate into our filtering equipment, some of it will be left on the glass. Glass is, while it appears soft, is often at the molecular level not, and some of those very fine particles will attract there, and that might affect some of our results as well. So looking at errors, what errors could happen when we're doing our experiment? Contamination with other species that may be there. Again, loss of our sample due to our techniques such as inefficient filtering. Have you spilt anything? The rinsing of the containers and rinsing them several times to make sure that we've got as much as we can out. Is there water still remaining in the final sample? So making sure it's dry and so forth. So let's have a look at an example. I'll move this down. So we've got a silver chloride precipitate collected from a 7.802 grams sample of peanut butter. So we've got 7.802 grams of peanut butter, and through a precipitation reaction we have removed some silver chloride from that peanut butter of 0.112. What is the percentage of the silver chloride in the peanut butter, assuming all ions are present as sodium chloride? So we've got sodium chloride. Obviously, our peanut butter is salty. So we've got sodium chloride actually in our peanut butter. And sodium chloride soluble. So we're going to add silver nitrate to that silver chloride, and we're going to form silver nitrate to the sodium chloride, and a precipitation reaction is going to occur, and we're going to get silver chloride, which is insoluble. And then we're going to get sodium nitrate, which is a soluble salt. So we're wanting to know how many moles of silver chloride. We've done the precipitation reaction, how many moles? Well, we've been told that there is 0.112 grams of silver chloride of the precipitate that we've got, and its molar mass is 1.43 times 0.32. So looking at that there, we have got 0.000781 moles of silver chloride that has been formed. Now looking at the equation at the top, we can see that there is 1 mole to 1 mole ratio between the sodium chloride and the silver chloride. So that will also tell you that there is 0.000781 moles of sodium chloride. So now how much mass of sodium chloride is actually in our sample of peanut butter? Well, to work out the mass, we've got the number of moles, 0.000781, times the molecular mass of sodium chloride, and we get 58.44. So in the original sample of 7.802 grams of peanut butter, there would have been 0.0457 grams of sodium chloride. And so that as a percentage, 0.0457 divided by the amount that we initially had, 7.802, and multiply it by 100 to get the percentage, and we've got 0.586 is the percentage composition of sodium chloride in that sample of peanut butter. So you can see how there it's used in even food industries to calculate the percentage. So of course you need to know your precipitation reactions and so on. Have a go at this one. And I'll move me out of the way again. So we've got a 10 gram fertilizer containing ammonium sulfate, similar to what we're doing in class at the moment. And it's dissolved, and we're adding some barium chloride. So the barium ions are reacting with sulfate ions to form solid barium sulfate, again what we're doing. Now neither the chloride or the ammonium ions will form a precipitate, so they'll stay in solution. The solid barium sulfate extracted by filtration and weighed, and we end up with 8.25 grams of barium sulfate. So we've got 8.25 grams of barium sulfate out of our original 10 gram sample of fertilizer. So using a similar process before, write out the equation. look at the equation that we've got. So ammonium sulfate plus barium chloride is producing barium sulfate and ammonium chloride. Write out your equation, look at your mole ratio. We know that we've got barium sulfate at the moment, so we can use that to determine the amount of moles. Have a go, and we'll talk about this a little bit further in class tomorrow. See you then.